Hey class, I wanted to start today's lecture by fixing some of the mistakes that I introduced in the last one, and then I thought we could finish our review of background concepts, maybe begin going over recursion and induction, and however much time it takes at the end, maybe 5 or 10 minutes at the end, to go over what we're what I would like for you to do for homework one, which should be available as you watch this video. Okay, so the yeah, let's jump into some of the proofs that I perhaps didn't take a critical enough view of before I presented to you, and we can explain sort of why they're incomplete as they are. They kind of rely a bit on, well, we'll go over that at the end. Okay. Okay, so whenever we were proving the case for n equals 2k, or n is some even integer larger than 1 for the Fermat's theorem, we had it in this form, and then we showed that, well, if it's an integer, then it should be generated by Euclid's formula, and so it has this form. But that was perhaps a little fast and loose. So it's true that if we make the assumption that these values are in this form, that this is necessarily a radical, but we can rationalize, or we can make b to the k into an integer, or b into an integer when taking the kth root of this, by separating out all of these other prime divisors, which are a multiple of k. Their exponent in the prime factorization is a multiple of k, so when you raise it to the 1 over k, it divides out evenly. But 2 kind of stands out, and so I have this criticism section here to show where the proof falls a little flat whenever trying to be rigorous, right? So we showed that if the others held true, then b was necessarily irrational. But it is possible to separate out some factor which is almost a perfect kth power of some integer, right? With this 2 to the L times k minus 1, where we show that it's just one term away, one factor of 2 away from being a perfect kth power, right? Something that is, its exponent is divisible by k. And so that could really rest with m, or it could rest with n. And then when that's the case, so it's true that all of the other prime factors have to have a multiple of k. But if we were to rationalize b, then it still remains to be shown that when that's the case, if we plug in this for m over here, right, or over here, that either this or this is irrational. So I've left it as open because it's not a truly rigorous proof in that standpoint. So it's almost there, but we're not sure whether or not we can even complete it. Right? Okay, and then for n, whenever it's on, and really this argument would have applied to the general case, which is I suppose kind of why I was so laxed on the other case for even. Right? Well, we showed that x and y, or rather whenever we solve for a and b individually, that we end up with values that are larger than the real and imaginary component of c whenever we take the root of c, and presumably theta here is on some branch larger than the principal branch. You can kind of make it to where it lands on some nearly equilateral triangle. And so we show that no matter what you end up with for the real and imaginary parts, you end up taking this exponent to, or cosine for the real part, cosine to the 2 over n, really, right? And sine to the 2 over n. And we know that theta falls in pi over 2 or whatever, and so in that range we're able to show that they're not equal. But we had gone through all that work to establish that that it would be a scaling triangle. And so in some sense it makes sense that A and B would necessarily be larger than the real and imaginary parts of C whenever we take that nth root. And so I'll show you, kind of what that looks like graphically. And in theory, it's possible to complete this proof. All that remains to be shown, and this is equivalent to Fermat's last theorem, is that for any choice C in that range, in that first quadrant, where it's not on the line y equals x, then you have A equals rho times the cosine of 2 over n theta, and B equals rho times the sine to the 2 over n theta. So we know that for n greater than 2, because of Weil's proof, that this is true, but we haven't shown it independently. And so in that regard, it's still incomplete. But the idea is that rho, this is the value of C. This is our radial value. And we're swelling out the projection on the real and imaginary axis to generate that scaling triangle. And again, I'll show you in just a second on the whiteboard. And so we know, because the theorem has already been proven, that it's true that at least one of these is going to be some either a fraction, which does not divide rho, or a more than likely an irrational number. And so if you can show that separately, if you can show independently that for n greater than 2, that one of these is guaranteed to be irrational, then you have that either A or B is irrational, or that n itself was irrational. And so the idea with Fermat is that one of them's got to give. So you can pick 3 of them and solve for the 4th variable, but it'll be some irrational number. And that, so you can fix whatever 3 you want, A, B, and N, or B, C, and N, or A, B, and C, and solve for N. But you can't have all 4 at the same time. Okay. So how do we solve for x whenever this is the case? Well, we solve for it algorithmically, essentially. So we want to know, x is on both sides. How do we solve for it? And so we can use something called the shooting method, and it's going to look a lot like our binary search whenever we go over that. And the idea is that we move everything onto one side, and whenever this is greater than 0, then this is greater than this, and whenever it's less than 0, then this is greater than this. And so in that manner we can decide from our inequality whether we've undershot x or overshot x, right? So if it's greater than 0, we've undershot it, and if it's less than 0, then we've overshot it. And so you just iterate x. You can just count x. You can do it by powers of 2. You can do it by counting 1, going 0, 1, 2, 3. And then as soon as you get something that's too large, then you have your previous guess, which was undershot, and your next guess, which was finally overshot. And then you start taking midpoints from there. So you have a lower bound, which was greater than 0, and an upper bound, which was less than 0. And then you just start taking the average of the lower bound and upper bound. And if it's less than 0, if it's greater than 0, then you've undershot. And so your midpoint, that guess that was between your previous lower bound and upper bound, becomes your new lower bound. And if it's less than 0, then you overshot, and that new guess, the midpoint, is now your new upper bound. And so you just continue to hone in on it by taking the average of your lower bound and upper bound and then replacing as appropriate. And so by hypothesis, if A, B, and C are integers, and you know that x is larger than 2, then you know that it's going to be some irrational value. And so you'll have to you'll never get it exactly, and so you have to define some error tolerance so that whenever the difference between these two is less than your expected error, then you've effectively found x, or you found a close enough approximation to live with. Okay, solving for b is the same thing. So in this case, our function looks like this, where we have b minus this x root of c to the x minus a to the x, and whenever it's whenever it's greater than 0, then we've undershot x, and when it's larger than 0, then we've overshot it. Okay. So if we're not sure if we're able to prove the n roots, or the 2 over n root of sine of theta and cosine of theta, if we're not sure that we'll be able to prove that those are irrational, then one alternative that we can look at is modular arithmetic. So Andrew Weil's proof, from what I understand, relied on modular forms and semi-stable forms of elliptic curves, which is a bit beyond me at the moment. And so I had hoped to kind of generate something that would be a little more intuitive, that we could understand, but it perhaps fell short in that regard. But if we were to look at modular arithmetic, and this is something that we'll look at when we discuss encryption, so I thought it'd be a good time now, then we see that, a modular set, in this case, the cyclic group with respect to C, is just the set of remainders that are possible when you divide a whole number by some number C. So if we divide any integer by 5, then 5 divides it, in which case the remainder is 0. It nearly divides it, in which case the remainder is 1. It can miss by 2, it can miss by 3, it can miss by 4, but if it misses by 5, then it didn't miss at all because it was divisible by 5, right? So it cycles over and over again, so that as you count up on the integers, everything falls into one of these categories. It's divisible by 5, it's in the first class of numbers that are missed by 5, where it misses by 1, where it falls short by 1, I should say, where it falls short by 2, where 5 dividing by 5 falls short by 3, and where dividing by 5 falls short by 4. And there's a fair amount of structure to these sets, so that you can manipulate these numbers. You can multiply just these 5 numbers, you can add them, you can multiply them, and you can find out whether a number that is divisible by 5, or a number that is has a remainder of 2 when divided by 5. If you multiply it with a number that has a remainder of 4 divided by 5, you'll end up with a number that has a remainder of 3 divided by 5. Likewise, if you added a number that has a remainder of 2 when divided by 5 with a number that has a remainder of 4 when divided by 5, then you would end up with a number that has a remainder of 1 when divided by 5. And so whenever you're discussing just the remainder, as we will whenever, again, we're discussing encryption, then you can really simplify your logic a bit to find out whether a number is divisible by it or not. And so the way this relates back to Fermat is that for every one of these numbers, whenever we're adding them together, we end up, we see that there's these pairs where if we add something with a remainder of 1 to something with a remainder of 4, we end up with something that is divisible by 5. If we add something that's divisible by 5 to another thing that's divisible by 5, then the whole thing is still divisible by 5. Likewise, remainder of 2 with remainder of 3, we get something that's divisible by 5. And then the product rules hold sway as well, so that if you multiply two things together that are not divisible by 5, then you will end up with something that is also not divisible by 5. And so, but if you multiply any of them with something that is divisible by 5, then the product is itself divisible by 5. And so you end up with the ability to add and multiply these numbers and end up with something that has a fair amount of structure. And so what we want to look at whenever we're discussing Fermat and we try and relate it to these cyclic groups, these remainders whenever dividing by something, is, well, let's consider C as this element that's dividing something. Okay? So then the sides of the triangles that we were looking at would have to fall in, because C was the largest side and we're dealing with integers. Then it would have to be one of these. Well, we know off the bat that it can't be 0 or 1 because one side has to be less than C, which would make it a maximum of C minus 1. And then if the third side was 1, then it wouldn't obey the triangle inequality. Right? So they would add up to the same thing, and as soon as you squared it, C would have overcome a squared plus b squared. Right? We'd already explained from the exponential forms that once it overtakes it, it never recovers. Okay, so we have something. So we have two sides that live in this set, and we know that they're not equal, and we know that they're co-prime with C because we're dealing with if it's not co-prime, we can factor it out of the equation, right? So all of the things that aren't co-prime, where a to the n plus b to the n equals c to the n, where they share some common multiple, those could be generated from some primitive solution where they are all co-prime. So we can just discuss that simplest case. So there's no common divisors, and we would say that they are generators of the set z sub c. Well, of all of these, it would never, raising any of those generators to the arbitrary power will never get you something this multiple of c because they're co-prime. Right? So we need to find two generators which are not inverses of themselves here in this first set. And we know that from Pythagorean triples that sometimes it comes out that there are these numbers, these pairs, that whenever you square them, you end up with something in this larger set, which instead of going from 0 to 1 less than c, goes from 0 to 1 less than c squared. We know that sometimes you end up with these pairs that do add up to something that is divisible by c squared, and in fact it would be exactly equal to c squared if it was a solution. Okay. And then we also know a few other things, right? So if it's going to have if it's going to participate in a solution, then it has to at least be, then both elements, either element has to be larger than the square root of c. Because if a squared is less than c, then you can't reach it. Essentially, the c minus 1 squared is the largest element that we can generate in this second set. And so anything that's less than c, right? So whenever you multiply that out, c minus 1 squared, it's c squared minus 2c plus 1. And so anything that is less than 2c minus 1 when squared is not going to have that perfect pair that allows it to add up to something that is divisible by c squared. So you can see how we start eliminating these elements pretty quickly. So before you've even squared it, there's certain elements that'll never be able to add up to something in a solution. And so the Fermat's last theorem is equivalent to saying that you can only generate those inverse pairs sometimes for c squared, z modulo c squared, but you can never generate it for c cubed, cn, or whatever. And so here's the formal statement of that. But the question is, what happens to it? What is it about taking it to some third power for all future iterations, all of these inverses are unreachable? We cannot create them by analogous elements, right? So here, the claim is that we can pick an element from G1 and it has some numeric value which is equivalent to some element from this second set or this nth set. So 0 through C minus 1, right? They're going to have these analogous values over here. And if you take it to any power larger than 2, the inverses simply aren't reachable. And I say that it's necessary, a necessary condition to prove Fermat's last theorem. I think it's also sufficient, but given given the last class, I didn't want to make any claims beyond what I could actually show. Okay, so part of this is that these inverses for these higher powers will end up being prime numbers, and so we won't be able to generate them from that initial set. Some of them are going to be composites of other numbers in the set. So like 2 times 3 times 5 or something like that, or 2 times 3 times 4. And so it's we could generate it from the elements, but not using powers. And so I find it interesting that I understand that it's an equivalent statement, but it's not something I'd really considered happening. It's just that those inverses could no longer be generated by taking powers, and so it says something about the spacing of these powers, and there are some other conjectures that also discuss the spacing of perfect powers and whether or not you can ever get 2 of them to add up to some third one whenever the powers are greater than squares. And so anyway, so I will post this now that I've highlighted kind of the flaws in the original argument, so you can read it at your leisure. But before we jump back into the lecture notes and before we start discussing homework 1, I wanted to go back to where is it? Yeah, this. And I wanted to show kind of how A and B are the swelling and sort of what I'm talking about. So, okay. Okay, so we picked 3 points, right? And we decided by convention that B would be the imaginary value. So let's okay, so this is our complex plane. We have points B, A, and C, which lie on the real line, and presumably these are all integers. And then we have this integer over here, A minus B. And so we can draw a circle of radius C around the origin. And then we can draw a circle of radius A minus B around the point A. And I'm pretty sure neither of those are circular arcs, but we'll deal with it. We'll make do with what we've got. Okay, and so this is our pseudo hypotenuse or whatever. It's our longest side in the scaling triangle, and then this is the projection down. So this side is of height c times the sine of 2 theta over n, and this is the projection on the real axis of c times cosine of 2 theta over n. And then a okay, so this is side B, and this is side A. And so the result that we showed was that this was always going to be longer than this. There was a swelling, essentially. And also that this, that A, the root part that lay on the real axis, would always be larger than this part. And again, that there's a swelling in that direction as well. Because whenever you take a root of some number between 0 and 1, you get something that is larger than the thing that you originally took the root of. And it's this overall tendency of roots to tend towards 1. So if you take a root of something that's larger than 1, pushes it towards 1. If you take something between 0 and 1, it again pushes it towards 1. And so we showed that they weren't equal, but that was kind of also what we were building up to as well, right? Oh, and this is theta over here. So what remains to be shown, if it's even possible to complete the proof in this fashion, is that B is going to be irrational. So we know by assumption that C is some integer. We also know by assumption that n is going to be some integer. And so what we need to show is that if you take some root 2 over n of sine of theta, where theta where theta is in the open interval pi over 3 to pi over 2, then right, and probably not closer to pi over 3 than pi over 2, but that's your restriction. Then whenever sine of theta is in that range and whenever cosine of theta is in that range, then taking the 2 over n root is irrational. So that either this side or this side would be irrational for any theta in that range and any choice n. And so you can attempt it, you can try and establish that result by taking the rational points on the circle in that range. And so their x on the unit circle, their x and y coordinates would tell you like when those are rational. And I think I can remember the formula offhand. So it's and so in this quadrant, it's going to be the points where Q and P are integers, and Q is larger than P, And then again, this formula should look pretty familiar because it's what we were dealing with the Pythagorean triples and the complex the square operation and complex variables. So it's the points q squared minus p squared over q squared plus p squared, and 2 times q times p over q squared plus p squared. And so if you can show that for this entire set of integers where q is greater than p, for all natural numbers, that either this, so this would be cosine theta, this first one, to the 2 over n, or this, which is sine theta, to the 2 over n is irrational, then for all choices q and p, then you would be done. But that we kind of started there, right? Like it's kind of if we could do that, then we would have been able to prove it directly from Euclid's formula. But it has transitioned the problem a little bit. But I don't know if it's done it sufficiently to be able to show that all roots of that formula can be shown to be irrational. It's still essentially the same problem. Anyway, so yeah, I just wanted to show you that the swelling or whatever, it was to be expected. We already knew that these sides would be unequal, and so you'd still have to show that it's irrational. So I think the modular, if you can find enough structure in the modular forms, then perhaps that's a better way to go and show why it is that it's only possible to generate those additive inverses from that initial set whenever squaring, and only sometimes. But I don't know. It may be that there's only these super very high level mathematical structures that are able to properly represent this problem. But if I will keep searching to see if there is some intuitive way. We have these statements that are equivalent to the theorem, so because it's already been proven, we know that they are true. But if you want an independent proof, then you have to prove one of them separately. And that is not always the easiest thing to do. But if I come across such a proof, or if I'm able to construct one, then I will definitely share it with you. So okay, I will post those with the criticisms that show why it's not fully completed for you to read. But let's jump back into our background concepts, and then we'll make sure we leave enough time to discuss the homework. Okay, so we left off with encryption and security. So encryption comes in two forms. There's symmetric encryption and there's asymmetric encryption. And the idea behind both is I have something that I want to share with some other user, but I don't want anyone else that's on the network to be able to decrypt it. So we talked briefly about how easy it is to execute a man-in-the-middle attack if you're on the same network, or just if you're one of the nodes along the way that's receiving and forwarding traffic, that you could also be capturing this data selectively. You're listening for some either source or some target IP or address, and you can select those packets and try and decrypt them at your leisure. So these two forms of encryption are fairly different, are extremely different, I should say. So symmetric encryption requires that both sides agree on the same key in advance, so that the same key that is used to encrypt the data is used to decrypt it on the other end. But how do you pass data in some trusted manner if the two sides have never spoken before, if they haven't been able to agree on some key in advance. And so asymmetric encryption is kind of the method that is behind Diffie-Hellman key exchanges and RSA encryption. And so we'll go over those in more detail, but the idea is that you can exchange public keys with another entity, and you multiply that with your private key. And so your public key is generated from in part from your private key. And so when both sides make this multiplication, then you end up with something that is common for both sides, so that they can both encrypt data using that. And so it's this really computationally intensive process, and you use it so that you can create trust with some entity and exchange some symmetric key. And the symmetric keys are typically smaller, and then you're able to encrypt data in a streaming manner much more efficiently than the asymmetric fashion. But hopefully we'll have a chance to go into all of that in more detail later. Hashing algorithms, we spoke about them briefly whenever we were discussing hashing tables. And there are limits to it. So the size of your hash will typically be 128 bits, which is obsolete, 256 bits, 512 bits, and you could go higher as well. But you're limited to the number of unique values that you can have in that hash table based on the number of bits. So it can represent 202 to the 512 unique bits if it's a SHA-512. So it is possible to have these collisions for these distinct values. But the idea is that it is a fairly large space, and that if you have file size combined with that you would never have a collision with those two data points. So a good hashing algorithm will be able to guarantee that. And then we talk about I noted the pigeonhole principle, but we'll go over that later. Asymmetric encryption and SSL certificates. Okay, we mentioned that asymmetric encryption, you have this public key that you pass, and you multiply your private key with the other individual's private or public key, and then those combined are able to generate some common key, which is private, which both of you hold privately without having to divulge your private key to the other individual, and you can use that to do a key exchange. But whether or not an individual is trustworthy, whether or not you should even, whether is there any record of them that can be tracked down, if they claim to be a certain website, how do you know that they didn't just generate their key themselves, and that they don't have some fake ID, essentially, that they've actually been vetted by some individual. And so if you go on Windows to the management console, you just type in run, and then in the run bar it's MMC, and it'll pull up the management console. Then you add, remove, you look at certificates, generally for the whole computer, and then you'll get a list of these, whether it's personal, but the one we're looking at is trusted root certificate authorities, and then there's intermediate certificate authorities as well in the revocation list. But typically it's just the root one that's populated, and then there's this chain, so the roots can issue intermediate authorities, and the intermediate authorities will have a signature that says, hey, I'm vetted, you can trust me because this was issued by this authority. And then the OpenSSL or whatever SSL software you're using will be able to verify that the chain is intact, that certificate C was issued by authority B, and authority B was authorized by authority A, and authority A is one of your trusted certificate authorities. So it's not just that these entities have SSL certificates stating who they are, it's that they've been vetted in some hierarchical fashion by these entities. So these entities vet their own private companies or whatever, their own intermediate authorities, and then those intermediate authorities will, whenever someone says, hey, I have this business and I want you to issue me some certificate, then they will call, they will see who is registered by the state as some officer for that company, and then they will speak with one of the executives of the company to verify that the individual attempting to obtain a certificate is authorized to do so, and verify addresses and so forth, so that there is this trust that's established. So there actually is some process to go through in order to get those SSL certificates that are trusted. Now you can create your own self-signed certificate, and in here you can add them. That's what these personal certificates are and stuff like that. Whenever you do that, you can tell your operating system, hey, you can trust this certificate because I know that it's trustworthy. Now, you want to be careful about when you do that, because then it means that anyone else with access to that same root certificate can pull some pretty nasty tricks on you. They can pretend to be anyone, essentially, if they have access to that trusted certificate chain. So, anyway, but I just wanted to show that it's not out of the ether that web browsers trust these other certificate holders. There is this process, and then whenever it's issued for a limited time, typically a year, or maybe up to 3 years or at a time. But there's again a good deal of process to go through. Okay, so those SSL certificates, they actually have values. They have public keys and encoded in them, and those are used to verify that other entities were that it was signed by that particular entity. So you can verify code signing, which is another feature that I imagine we'll talk about later. Or, well, I guess we can talk about it now. So Mac, which is the only one I know of that's currently taking advantage of code signing, but I believe Windows can take advantage of it, but right now they just verify it. But the idea is that processors, modern processors, have this no execute bit that can be enforced if the code has been modified from the version by whoever signed the code, essentially. So it's possible to take a hex editor and change the bits in a particular piece of code, so that if you have a virus or you've been attacked by a worm or something like that, something has gotten into your system, and they want to monitor your keystrokes, or they want any form data to be passed to some other entity or whatever, they insert their own hack, and whenever that program is executed, then their code is being executed as well. But whenever you publish your code, whenever you build it, you can take one of these SSL certificates and you can use it to create a hash that is unique to your private key, right, and can be verified using your public key, and it gets stamped on to the code. And if the hash doesn't match what is generated whenever verifying it with the public key, which is against the publicly held certificate, right, the publicly available certificate, then you know that the signature has been changed. Or if the code doesn't match the hash, whenever you run it against that same certificate, then you know that the code has been changed. And the modern processors have this no execute bit that can test for that, but I don't believe that the practice of code signing is prevalent enough that anyone other than Mac is currently enforcing it. And so something that has been code signed on Mac operating systems is essentially guaranteed to be unmodified from whoever published the code, which I think is a really cool feature, but it creates a bit of a learning curve to develop on Mac. Okay, so that's the certificate authorities. Certificates are generated in a chain. Later in the semester, we'll go over the process of creating SSL certificates. And we'll probably end up spending more time discussing asymmetric encryption at that point. But the one of the key takeaways, though, is that even though RSA is the key to HTTPS encryption, it's because it allows you to perform this key exchange where you can agree on some AES key, and then that key is what's used to actually transmit most of the data for your web session. Okay, and then also I should mention that there are other forms of asymmetric encryption other than RSA, and that's elliptic curve cryptography. If I get far enough, I will include that whenever we discuss it. But that may have to wait for a future semester. We'll see. Okay. So then symmetric encryption and diffusion of information. Okay. So symmetric encryption relies on both sides having the same key. So if you are visiting some website and you perform the key exchange, then you are using symmetric encryption for most of the traffic. It's just that initial handshake where you agree on some secret to use to encrypt and decrypt the data that you use asymmetric encryption. But the rest of it is symmetric. So what is symmetric encryption? Whenever we talk about a key, what is it? Well, the simplest form is the substitution cipher or the Caesar cipher. So the kind of encryption that Julius Caesar used to send messages to his generals and stuff. And it's also the easiest to break. And it's because if you perform cryptanalysis on the ciphertext, then you'll see that the letters occur with a certain frequency. So there's sort of a fingerprint of the language that's embedded in that text. And so in English, the letter E is our most used letter. And in fact, in Wheel of Fortune, right, R, S, T, L, and E are the letters that Pat Sajak always uses as the initial guess to get the contestant started. And it's because those are it's the most frequently used vowel, and it's the most frequently used consonants. And so if you had a long enough ciphertext, then you would expect that in order of frequency, the letter in the substituted text or whatever, in the encrypted text, the letter that appears the most often, whatever it is going to be associated with E. So then you make that substitution, and then going down the line, you try these replacements, and if it makes sense, then you keep it, and if not, then it only takes a couple of cracks at it. But the language itself, the language that the clear text was written in, is going to leak information in this format. And so it's not enough to make this substitution. You can break it. And even something more sophisticated, like the Enigma machine from the German intelligence in World War II, was I believe they cracked the new code every day, even though it was updated every day, because there were these commonly used phrases. And so it was something very similar to this concept, where you take something that you expect to see, and then you're able to break it. And so, they would look for keywords like the weather report or Heil Hitler or something like that, which it seemed to be mandatory in these messages, and and that just that known value sort of allowed them to get the ball rolling on breaking the text. And so, if you ever find yourself on the code breaking side, then that is something to look at. Is that you can take something that you know will be there, and then use that as sort of this way to break it. So, whenever discussing symmetric encryption, AES is the current standard for the Department of Defense, and the size of the blocks that can be encrypted they are 128 bits, and then the keys are 128 bits, 192 bits, or 256 bits. And then that sort of affects the number of times that you loop through the algorithm in order to perform certain actions. And I describe it a bit here, kind of what it entails. But even something as sophisticated as this, in order to break the encryption totally, then what you want is you want to get the key. You want to break the key. And so if you were to, if you knew some hint about the information that was being transmitted, then you could attack it pretty efficiently, or more efficiently. So, for instance, like if you knew that a PDF was being sent, and you wanted to use certain information about the PDF to crack it. So this is a mistake that, I wouldn't call it a huge mistake, but the PDFs have a certain amount of header information in them, and then if you naively begin on the same block every time, like if you don't have some throwaway bits at the beginning, which this is something that can be fixed on the encryptor side, and then the other users or the people attempting to crack it are easily foiled, right? But if you always begin at zero, at byte zero, then just as the weather report for the Germans may have had, in World War II, may have had some prefixed data that you could always try and line up, and then you find the correct substitutions. If you have ASCII characters, then the first 16 bytes, right, if those always repeat, then you can break the individual's key within those first 16 bytes. And so that's why you would probably want to use a 256 I don't know if a 256-bit key would necessarily fix it, but the idea is that it's encrypted in these 16 bytes, and so if you do not randomize that first bit of information by having some offset, some agreed upon number of throwaway bytes, then you're helping out the hackers or anyone attempting to crack your code. And then on the flip side, if you are the one cracking it, then that is the key, is that you want to find anything that is form-fitted data, and then use that to your advantage in order to try and obtain that key. Okay, so there's a brief description there. We discussed code signing a bit and how it uses the RSA private key to create a hash based on some input file, and it essentially stamps a fingerprint on it, and it ties the binary code to the hash to the public key so that it can all be verified together. Okay, so now we want to discuss scalability, right? If you do your job well, then you've created a piece of software that is usable, it's enjoyable, and people want to use it. And because it's software, the number of users can exceed the available amount of support for it, right? So if you were selling some widget that has to be manufactured, then as soon as you sell out, then that's it, right? So your concerns are ramping up production and making sure that you meet demand, and then making sure that you don't overshoot it and crash the market for your widget or whatever, right? So it's a different set of concerns. For software, you create the website or whatever product, but if it is a website, then you have to worry about scalability, so the number of simultaneous users that are accessing your system. So it's easy to sign up. They all want to access it during the work hours, during the workday from 8 to 5. And once you go from 100 users to 1,000 users, you start to see a set of problems that you didn't see at 100 users, and that you certainly didn't see when it was just a small development group accessing it. And then when you go from 1,000 users to 10,000, 10,000 to 100,000, 100,000 to a million, then you really start to see a lot of different stress points, and it's a series of things that were previously working that do not function at scale. There's just these constraints on resources that you didn't really take into account whenever you were developing it, but now you have to. And at the same time, it also doesn't make sense to spend a whole lot of time optimizing for 10 million users, spending a year to optimize for 10 million users, when the company will fold if you don't get to 1,000 users within a month or something like that, right? So you have these conditions, these time conditions, that are forcing you to write code that is good and usable, and that the user will enjoy and recommend to others, and will hopefully create these problems at scale in the future for you. But you have to write that quickly, and then also know where it is that you're going to have to go back later on and modify to make it capable of supporting more and more users. So that's the job. Like in a best case scenario, that's what you've done, and you have to do this race. And as you begin to scale up, you'll get more people added to the team, and so all along the way you need to keep in mind that the code that you write is sort of just for right now, and if it's good enough, if you've done your job well, then it'll be modified or thrown out or replaced completely by something else. And it doesn't mean that it wasn't written well initially. It just means that you didn't write it for something that didn't make sense at the time. You didn't write code to support 10 million users when you really only needed to support 100 users, or you just needed to get some initial account, and so really all you needed was to be able to demonstrate something. You just needed a proof of concept. And so that's why it's going to be key to write maintainable code, because almost everything you write will be replaced sooner or later. And it needs to be really clear what it is that it's doing and why and how it's doing it, so that whenever they come along later and say, okay, well, this is some stress point for whenever we're trying to support this larger number of users, I need to know exactly what it's doing so that I can replace it with something that's capable of supporting many more users. Okay. So strategies with dealing with really large numbers. One of the things that is a fair number of sites seem to be trending towards is REST APIs. So first, you separate the process of presenting the site with the actual code behind it. And so the popular way to treat this problem is to use a single page application, or a SPA, which you'll hear of. And that will act as kind of this application that's run inside the web browser. So it's mostly JavaScript, and it knows how to construct HTML elements and how to present the data, and it has all of these stylings so that everything has this common feel to it, and it feels exactly like a website written in just HTML and CSS, but it's very interactive, very smooth. There's very few delays, and when there is a delay, it doesn't feel like the application has stopped while it waits for a response. It shows you one of the waiting logos or whatever. I can't think of the word at the moment, but anyway, it gives you the waiting icon, and but the rest of the site is still usable, and so that the user gets their feedback immediately, and then everything else kind of happens in the background, and nothing happens more than once, and so forth. And so whenever you create that layer of indirection, now the servers, so you have some edge servers that are basically serving up the index.html and the JavaScript and the CSS and whatever images. And so none of those are hosted by you. You put them out on some other service that is able to quickly serve it, and it doesn't require any back-end support. But the single page application that you've created will know where to look for your service. It'll have the URL essentially, and so it'll make all of its API calls there. And so in order to support some scaling number of these API calls, which scale in proportion to the number of users, you create something that doesn't have to be maintained continuously. So one request can go to any arbitrary server. It doesn't have to be the same one every time, and then that server is able to service the request and send the response back. And so that pattern is known as a REST API, and so it is a stateless API, representational state API, something like that. I forget exactly what it stands for. And so this really seems to have overtaken sessions and the initial web forms from .NET, .NET web forms, where you would send state in this hidden variable, and the state could get to several megabytes. And so the idea is that you have some token that authorizes the user, some JSON web token that authorizes the user, and so authorization is handled in the header of the request, and then you call directly to the correct endpoint, and that the single page application that you've created knows exactly what the correct endpoint is, and then that will have a pre-formatted set of variables that need to be provided, and then you will get some pre-formatted type of response back. And so that you've really relieved the server of having to figure out what it should look like on the front end. It doesn't have to generate the HTML anymore. The single page application handles all of that. And the server is really just there for data transfer. So now you have these chunks of data that come into your web page, and your JavaScript is able to make that presentable because it knows the format of the data, because the API is well documented and so forth. And so whenever it gets a response, it knows exactly how to present it. And so these are patterns that you're going to want to learn beforehand and kind of develop the habit of using, so that you don't have to reinvent everything. So again, the emphasis all along the way is to create maintainable code, and part of that is identifying these design patterns for whatever type of application you're going to use and create, and use those, and then substitute pieces of them as you need to make things more scalable. But I have used the single page applications with REST APIs in the background, and it's glorious. It's really the only way to do it right now. I mean, maybe someone will eventually come up with a better way, I'm sure. That's kind of the way that the industry innovates. But for now, it just makes sense to separate presentation from the data that is being persisted, and whenever you retrieve it. And so it once you learn how to think in that fashion, it becomes very manageable and intuitive. Okay, so then orders of magnitude, we discussed that a little bit a couple lectures ago, where depending on where the information lives, it's going to cost you another factor of 10 typically to access it. Okay, and then practice. In order to be good at any part of this, you kind of have to not be miserable, right? So you have to find what it is that you enjoy about programming, and maybe it's the end result. You like having created something, and you like being able to see it or show it off. Maybe you enjoy the process itself. Something about it just feels kind of like putting the universe in order. And so whatever it is, try and focus on that, so you enjoy yourself along the way. But you have to do it pretty regularly in order to be any kind of good at it. So I recommend that if you're going to do this, and that you start now by creating a GitHub account, or on your own computer you can use Subversion, but GitHub is good because you can include it on your resume whenever you start applying for jobs. And then you have to learn how to use Git, and it's pretty simple. So you'll have a main branch, and then you'll have your account, and then your account can create multiple repositories within it, or multiple projects, and then each project can have its own branches. So you'll have the main branch, and then if you have some new feature that you want to try out, then you can create a new branch, and it'll copy everything from that trunk or your main branch into that new branch, and you can make your changes. And if you decide that you've broken everything and you don't feel like reverting, then you can just abandon that branch and go back to main, and it tracks it for you, so that you don't have a billion files on your system tracking these changes. But go ahead and create a GitHub account now. It's really easy. Alright, so you go here, you go to sign up, pick a username, put in your email address, password, it'll verify everything, and then you go from there. And so start working with it now, because whenever you apply for a job, if your prospective employer thinks that you won't use source control, then they will put your resume at the bottom of the pile, and it's important to give yourself a chance. So learn how to use Git, and you can use Subversion or some other version of source control, and that'll at least get you started. But again, this you can put on your resume, and they can see the work that you've done, and it is a step in the right direction. Oh, and then here in bold letters, never check in code that doesn't compile. So you made some brilliant changes, you added a feature, and it almost works, and you don't want to lose it, but it doesn't compile, and you don't know how to fix it. Okay, well, then don't check it in. If it doesn't compile, don't check it in. I don't really know what else to say to you about that. It's fine if you want to copy it to some temporary file and sort of try and implement the changes again one by one. But if you've gone so long between compiles and you don't have the experience to just fix it offhand, then you should probably look at just tossing the change, right? You might say, well, I worked on it for a week, and I don't want to lose all of that work. If you worked on it in a week without compiling, you should throw away the work. Compiling should happen fairly regularly. Whether or not you check it in, all the time, that's a different thing. But whenever you have these long-running changes, again, developing good habits is going to be key to being a good developer. Create some branch, some offshoot of your main branch that can track these changes, and then compile frequently, and check in every day into that branch. You don't have to feed it back into the main branch. You don't have to merge the code, but check in every day and keep those changes going. But if at the end of the day it doesn't compile, well, if you've been checking in every day and you follow this rule, then you're never more than one day lost, right? So even if you have to discard everything you've done that day, it's still just one day's work, and you kind of already know what you want to do. So it's not a total loss. But if you check it in and it doesn't compile, and people start checking in on top of that, then you've created a nightmare scenario, and it's not clear where you have to go to fix it. And everyone has to stop checking in. So now the entire team's progress is halted because you checked in broken code. So just don't ever do that. It's better to lose the work that you've done if it doesn't compile than to check it in and have to deal with it, later. Okay. That's the end of that rant. Project management. So, Jira exists for small teams. Like, you can get that for free for teams of like 4 or 5 or something like that. And then there are sites like Monday.com and other project management sites. And so if you're serious about developing a project, then I would look at something that can track issues. So you'll get together, however small your team is, even if it's just a team of 2, or even if it's just a team of 1, and you'll make a wish list kind of all of the things that you wish could get in, and then you'll break it down into things that absolutely have to be there, and then things that you will get to later. So the things that you absolutely have to have typically are going to be, if it's a website, you're going to have some private area. And so you need both the public site, which may be simple and bare bones at first, but you're going to need that, and then a login page. And you might prioritize the login page so that you can you can split up the work between the public site and the private member area, and so that is your first list of tasks. And then based on what it is that you want your site to do, then you have all of these other wish lists. And the way you track that and prioritize them is through some project management application. And then that'll allow you to say, okay, well, this thing has to be completed before we can do this, or we have to purchase this piece of software before we can complete this task or whatever. And so it allows you to continue to refresh your memory of why you haven't tackled certain things. And other individuals can come along and say, okay, well, I can't do that, I can't do that, I can't do that, let me take a look at this, and so forth. And so it sort of sets the table for adding members to your team later that can help contribute, and it gives them a way to sort of peek into your thinking in order to tackle those problems. Automated tests are a good idea. I don't believe I've ever worked on a project with a set of front-end tests. In theory, it can be done, but usually, you work with the imperfection. So you are young, you're in school, I would highly encourage you to learn how to create those front-end tests for the user interface. But if not, they manifest themselves pretty quickly. It becomes really obvious that something is broken in these cases. And so, we've always shortchanged the front-end test, but again, if you can do it and you have something that's a really tricky feature, or if your front-end code is game development, then you will probably want a test suite for that. But back-end code, it's pretty easy to write the tests for those. I think we have a project where we'll be able to show some of the back-end tests and what those unit tests look like. But if not, again, it's something that you can look at and pick up. And so, but the idea is that you are testing the units of your code, the functions. So the functions should be fairly simple. You should be keeping everything fairly simple. And then the unit tests are a way to enforce that they don't change in an unexpected manner as people modify the code on an ongoing basis. So you kind of lock in the behavior by adding these unit tests, and then they get run every time there's an automated build. And if the unit test breaks, then an alert is sent out, and you can say, oh, well, someone changed some functionality. And the idea behind the unit tests is that they test sort of 3 different things. So they test valid input, so that valid input ends up with a valid output. They test edge cases, so that something like here, if we're squaring a number and we're dealing with 32-bit numbers, that if you pass in something that's too large, that it provides a consistent and expected result. In this case, an argument out of range exception. So it's too large of a number to square into an int. And then, so it forces you to document how you're going to handle exceptions from one. And then for invalid input, so if you pass in not a number and you attempt to square it, you get an invalid argument exception or some equivalent. So valid input, edge cases, where it's a valid input but not something that you can handle, and then invalid inputs. And so those are kind of the 3 typical categories that you'll deal with. And the idea is that you can't make your code run for all scenarios, but you can make it fail in expected and consistent manners, which can be considered to be correct for that case. And so unit tests are a way of forcing you to think that through. And then automated builds and deployments. So the idea is that if you have some common source code repository, like everyone's working off of the same GitHub repository, then everyone's checking into the same place, and you have something that listens for updates. And then whenever a change is detected in the source code repository, then it downloads the code, it builds it, and then it sends out the all clear if every test passes, or it sends out an email saying that unit tests have failed, someone needs to look into it. And then automated deployments are these like predefined scripts, and so the builds will build it and they'll leave behind some artifact, and then you have the option of executing one of these scripts to deploy it either to some test server or some development server or a QA server or a production server, which you'll probably use some other process in order to deploy to some alternative production server, and then you perform the switch, or you do some forget what the name is, like red-blue testing or something like that, or A/B testing, where you have some feature that you've enabled, and some of the users will go to that new feature, and some of the users will not, and so forth. But it's the idea behind automated builds and deployments. And then we'll discuss proofs later on. Okay, so Overleaf. So now dealing with your homework really quick because we're already over. You'll go here, you'll pick out some email account or whatever to work with, and then you sign in with that, and you'll create the account, and then I don't want that one. Hold on just a moment. Do I have this one set up? Not registered. Okay, well, whatever. So in theory we would register that. So here we'll go ahead and we'll log in with this, and then we'll get a bunch of stuff, but we'll create a new project, and we'll call it homework 1. Right, and so you'll take the tech for homework 1, copy it, and you can use just Notepad or whatever to get it, and then paste it in here, and let's see whether or not yeah, okay, so there and so forth. Okay, so then you'll go here and I'll say that your name is some name, right? Presumably some correct name. Let's include your middle name here. Right. And then that'll appear here. And then all of this header stuff, or all of these directives sort of include like packages and stuff that we need to use. But we won't necessarily worry about that. So once you add your name, then you'll come down here to problem 1, and you'll read the question using induction and so forth. So there are notes on induction, and we'll go over this in more detail and kind of make it easier. But I give you this example problem. Yeah, and then we'll do this one. So that's the idea. That'll get you started. You can use Overleaf to create these. It's free to sign up for the account. And then whenever you're done, you can download the PDF. And then to copy the code, right, you just highlight it all, copy it, and stick it in Notepad, or oh no, that was terrible. What have we done? Well, not Notepad. Use Notepad++ or something else, right? And then save it as homework one dot tech tex. So save that. Okay. So that's enough to get started. If you're completely lost on the homework, well, you should be less lost on Tuesday when we go over it. But that's how to use LaTeX. Again, there are notes on it on dealing with these, and I might upload a little helper video to kind of help you along, since we didn't get as far into it as I had hoped to whenever we started. Anyway, okay. Well, have a good weekend. Good luck with the homework, and we will talk on Tuesday.